Hey guys, welcome back. I'm going to go over some of the notes for sound. And this slide is the slide for the beginning of waves as well. So I put those two together, even though waves are halfway through the simple harmonic motion. To me, simple harmonic motion belongs by itself, and waves and sound belong together. So just to review, our motion of our disturbance is going to be a wave, and if you have a mechanical wave, it needs to have a medium. Sound requires a medium, and I explained this to you guys previously where we get this call from the Alien movie, No One Hears You Scream in Space. So because there are no particles out there, it's impossible for sound to travel through space. Essentially, sound requires an object that's vibrating to bump into the next molecule next to it, which in turn bumps into the next molecule and causes it to shake on down the line. Well, there's nothing to shake, then you can't have any kind of sound. That is the truth that space movies like Star Wars, where when they're showing people shooting lasers from ship to ship and it's pew, 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 really should just be silent, even though it wouldn't be as satisfying. So this is going to be vibration. This is what it looks like close up on a record. And I'll show you guys in person what this looks like. And as the needle goes over these disturbances in here, it vibrates. And that is what you hear. There is a misconception that sound doesn't travel well through solids. That's not true. So the closer that stuff is together, the faster the sound is going to go through it. And so since air is gas, it's going to be slower than if it is going through liquid. And liquid is going to be slower than if it's going through solids. It also matters what temperature it is. So if it's very cold out, the particles that the object's moving through, their kinetic energy to start with is going to be lower. And so sound is going to travel slower. If it's hot out, the opposite would happen. Those molecules would be more excited. Our elevation also matters. If we think about, if you're at a very high elevation, the air is thinner, less molecules, and the sound is going to slow down when it travels through that as well. So here are some of our examples. So if it's air, they're saying that it's 343 meters per second, and then they have it at 0 Celsius. So this is at 20 degrees Celsius and 1 atmosphere. This is at 0 degrees Celsius, and you can see it slows down noticeably. Remember meters per second to miles per hour, we multiply by 2.2. Then we see like just through helium, just through hydrogen, through water, through seawater. Then we have iron and steel, and it goes through. All right, so loudness is going to be related to the intensity of the sound wave. Pitch is going to be related to the frequency, and I'll do a demonstration with this as well where I show you guys what the pitch is. Higher pitch is going to be higher frequency. And again, we're still going to be looking at the relationship between frequency and wavelength as being an inverse related. So if you have a high frequency, you're going to have a short wavelength. And if you have a low frequency, you're going to have a large wavelength. What we can hear, and we'll test this in class, is between about 20 hertz and 20,000 hertz. But someone my age can't even hear up to 20,000. at some point you start losing your ability to be able to hear. Things above what we can hear are called ultrasounds. And if it's below, we call it infrasounds. So that's going to be sounds below 20 hertz. The intensity is going to be related to the energy per unit time, almost like a power thing. And again, this is going to be directly proportional to the square of the amplitude, and it's going to be inversely proportional to the square of how far away you are. And that's all we really need to know. You don't really need to know a lot about decibels. So what happens when I speak is that I am vibrating the air. I'm causing a disturbance in the air, and it's causing molecules to get closer together, and they affect the ones next to it. And like I showed you guys with the spring, it's going to move its way down. Once that disturbance gets to your ear, it causes a vibration in here, which you perceive as sound. And I have a couple of videos that I'll show you. So our eardrum vibrates, and the hammer, anvil, and stirrup are going to transfer those vibrations to the inner ear. And then inside of there, it's transformed into electrical signals that you guys can hear. And what happens is that as we get older, the ones that perceive the higher frequencies stop working. All right, so we're going to look at a number of standing waves with sound. And I'll do demonstrations for you guys in person. Well, you can have vibrating springs. You can have vibrating membranes, which would be like a drum, surface of a drum. You can have vibrating metal or wood shapes. So that would be like a xylophone. Or we can have vibrating air columns, which could be like an organ or a flute. And this vibration can be started by all sorts of things that are just causing a disturbance that is a given amplitude. So a guitar string, based on the string you have, you can adjust its tension with these little dials here, right? You can make it faster or slower by tightening them or loosening them. And then you can also, based on what guitar string you've had, you ever notice guitar strings, they have varying thicknesses. And so that's going to change the linear mass density, how much mass there is per length. And so you can affect the velocity by that. So once we have this is going to be equal to the frequency times the wavelength. And then again, you can change what your wavelength is by moving your finger. And there are lines here so you know what you're moving into. And so because that velocity will be set by you tuning the guitar, tightening it, you can make different frequencies in the same guitar string, and thus different notes. And again, this is our first harmonic, and so our wavelength would be twice the length, right? It's a half of a wavelength and then a half of a wavelength back. In a piano, there are varying lengths. If you notice the shape of piano. The wind instruments are going to create sound through standing waves in a column of air. So a tube open at both ends. So I'm going to again go over how to calculate these harmonics for you guys. And again, I don't subscribe to memorizing equations. I would like you to visualize what's going on in there and be able to replicate what the drawing is. So if we are open at both ends, because closed at one end is going to be different. This is going to be the same as a string fixed at both ends. So what do I mean by that? If you remember a string fixed at both ends, we had a half a wavelength down and a half a wavelength back. So our wavelength was equal to 2 times L to start with. And then we need to have that constructive interference again to get the standing wave. And so in the second one, the wavelength was equal to the length. And now we have 1.5 wavelengths. So our wavelength is 2/3 of the length. This is going to do the same thing. So our first harmonic is going to have the length times 2 is equal to the wavelength. And it's going to have a half a wavelength inside of there. And again, I'll do this for you guys in class, and we'll see the Julius Sumner Miller one. The second one is going to have an entire wavelength in there. And again, sound waves are not transverse waves. So even though our representations it's easier for us to draw transverse waves, really sound waves are going to be areas of stuff where they're pushed together, areas of compression, and then areas where the molecules are spread apart, areas of rarefaction. So this one is going to have an entire wavelength in. And then just like this had standing waves, this is going to have 1.5 for the third one. And again, once you have that fundamental frequency, you can just multiply by that first given value to get whatever harmonic you want. And I'll do a number of these for you guys in class. So this needs to have a whole wavelength and a half a wavelength. And then and again, it's going to be 2/3 of the length is the wavelength. And so we're going to say that this is F1, 2 times F1 is F2, 3 times F1 is F3, and so on. These are going to be our harmonics. All right, find the first 3 harmonics for, I'm hoping that's supposed to say a tube, for an open at both ends tube that's 0.23 meters long. I'm going to take the speed of sound as 343. because that's what it was in our chart. We'll assume that it's 20 degrees Celsius in here. I feel like it's much colder. I'm freezing all day. All right, so I know that for the first harmonic, that twice my length is my wavelength. And so this is going to be 2 times 0.23 or 0.46 meters. So frequency is going to be the velocity divided by this. So I'm going to have 343 divided by 0.46. And I have 746 hertz. Now, to go to the next one, there's 2 different ways. One is to remember what the picture looked like. We had a half a wavelength and a length, and then we had a whole wavelength and a length. So I can say that, all right, now for F2, L is equal to the wavelength. And so now F2 is going to be 343 divided by 0.23. Which I have as 1491. Or I can say that F2 is 2 times F1, which should be the same if we ignore rounding. And then for the third one, F3 should be 3 times F1. And this is going to be 3 times 746. Or 2238. Or you can say that the wavelength is going to be 2/3 of the length. So you're going to have 0.5153 meters repeating. So I'm going to have 343 divided by that, which I got 2237.